This is an excerpt of a past video on sound waves. It talks about the sonar Doppler effect. So students and friends, stay tuned, watch and learn. This sound phenomenon was first introduced by an Austrian mathematician physicist by the name of Christian Doppler. So what is this Doppler effect? We say that when a source of sound and a listener are in motion relative to each other, the frequency of the sound heard by the listener is not the same as the source frequency. Our first situation, if the source is moving towards stationary listener, as shown in this illustration, supposing this is the source of the sound, all right, the police car with its siren being blown, all right, and then there is this stationary listener, this man to the right, all right, what's going to be the what do you call the frequency of the sound heard by this man? All right, as shown in this illustration, all right, this listener actually notices what we call a high frequency, all right, a high frequency, because what happens is the wave fronts, all right, the sound wave fronts approaching him are getting smaller. So small wavelength corresponds to a high frequency. And mathematically, we can use this formula, all right, to determine what the observed frequency FL will be. It's just equal to the product of Fs. Fs is the frequency of the source of the sound multiplied by the ratio. The ratio tells us that the speed of sound in still air is to be divided by this speed of sound in still air minus the speed of the approaching source. And this, if you're going to analyze this well mathematically, we will come up with a ratio, all right? The number inside the parentheses will be a number that is greater than 1. And that will mean that FL will be greater than Fs. And that is the reason why this stationary listener, all right, the man, will be observing a high frequency compared to the original, a higher frequency compared to the original frequency of the source. Okay, situation 2 is if the source is moving away from a stationary listener. So using the same sketch, we have this uh, stationary listener, this lady observer, who is behind the car that is moving away from her. All right, so the source of the sound is receding or moving away from the listener. All right, and the frequency or pitch that will be heard by this observer is a low frequency sound or low pitch. That is because the wave fronts that are emitted by the source, okay, when they reach the observer, they are somewhat stretched. In other words, the wavelength, all right, of the sound is long, corresponding to a low frequency or pitch. And mathematically, the FL can be determined by using this formula. Okay, FL is equal to Fs multiplied by V over V plus Vs. Right? This means that since the source of the sound is moving away from a stationary listener, notice that in the denominator we have here B plus Vs, right? The listener is stationary, so you don't see the quantity here. You don't see the VL quantity because it is zero, right? So if you are going to analyze this further mathematically, you will find out that the ratio inside this parenthesis will be a number that is less than 1, which means that the observed frequency FL will just be less than or lower than, all right, the frequency of the source. F1 is less than Fs. Now, for situation number 3, this is when the listener is moving towards stationary source. Using another sketch, we have here the stationary source and the moving listener or observer approaching the stationary source. So again, because the observer is moving closer to the source, the wave fronts reaching him will be compressed, resulting to what we call short wavelength. Short wavelength also means higher frequency or higher pitch. And mathematically, the formula for finding the FL is just equal to Fs multiplied by V plus BL divided by B, right? Notice that in the numerator, we have B plus BL, all right? It is because the listener observer is moving towards the stationary source. That's why it is B plus BL. And the source is stationary, so you don't see the quantity Vs in our denominator. And analyzing this further, the quantity inside the parentheses, after being divided by V, will come out to be a number that is greater than 1, which means that the observed frequency FL will be greater than Fs, or the frequency of the source. The fourth situation is when the listener is moving away from stationary source, right? So in this uh, illustration, we have the source that is stationary and the observer or listener is moving away or receding from the source. So again, because the observer is moving away from the stationary source, what happens to the wavelength of the sound reaching him is that the wavefronts of sound are getting more stretched, resulting to longer wavelength, and that corresponds to shorter or lower frequency or lower pitch of sound. Mathematically, okay, the frequency observed by the listener is equal to the product of, okay, the frequency of the source multiplied by a number, right, the ratio, where we first subtract the speed of the listener moving away from the speed of sound in still air, then divide it by the speed of sound in still air, which will result to a number that is again less than 1, and therefore FL would be less than Fs. Alright? So, if we are going to combine all the equations, the four equations for the four situations that we have presented, we can come up with, all right, a formula that considers all possible situations. All right, this is just a formula, a shortcut formula, okay, to help you uh, if you are trying to memorize all the formulas in the different situations. Probably this is a better way of memorizing just one single formula which fits all the four situations or other situations that we have not covered. The formula simply goes like this. All right. So the observed frequency FL is just to be multiplied, all right, or is equal to the frequency of the source to be multiplied by this factor or ratio inside the parentheses. All right. We have the speed of sound in still air plus minus the speed of the listener, right, divided by the speed of sound in still air minus or plus the speed of the source, right? So we have defined the meaning of each of these quantities earlier, but I'm presenting it here again. All right, there you go. Question now is, when are we going to use the plus sign in the numerator? And when are we going to use the minus sign? Likewise, in the denominator, when do we use the minus sign and the plus sign? All right. So, for the velocity of the listener relative to the medium, usually the medium is still air. All right. You're going to use the plus sign in the numerator if the listener is moving towards the source. All right. Whether or not the source is moving or at rest. As long as if the listener is moving towards the source, you are going to use that plus sign in the numerator. You will use the minus sign if the listener is moving away from the source, either a stationary source or a moving source. Okay, now how about the signs in the denominator? All right, so that pertains to the speed of the source, or should we say velocity of the source. We use the plus sign, oh wait, we use the minus sign, all right? We use the minus sign if this source is approaching the listener, all right? If it is approaching the listener, moving towards the listener, all right? Regardless of whether the listener is at rest or also in motion, as long as the source is moving or approaching that listener, then you have to use the minus sign in the denominator. We use the plus sign, all right, if the source is moving away or receding from the listener, all right? So, uh, you might ask, why is the minus sign written above the plus sign in the denominator? Answer is, the plus sign in the numerator, which is written above the minus sign, you will notice that that plus sign suggests that the listener is moving towards or approaching the source, right? And the minus sign written above the plus sign in the denominator also suggests a source that is approaching or moving towards the listener, all right? So you see, the sign written above, all right, both in the numerator and the denominator suggests approaching listener, and in the denominator, approaching source. And look at the sign below. In the numerator, it is minus. In the denominator, it is plus. So, that minus sign in the numerator suggests that the listener is moving away or receding listener. And the plus sign in the denominator, which is written below, all right, also suggests that the source is moving away from the listener or a source that is receding from the listener. Question number 1. Police car's siren emits a sinusoidal wave with frequency Fs equal to 300 Hz. The speed of sound is 340 meters per second and the air is still. the siren is moving away from the listener with a speed of 45 meters per second relative to the air, and the listener is moving toward the siren with a speed of 15 meters per second. Question is, what frequency does the listener hear? Right, so that is illustrated in our uh, figure here or sketch. All right, so the listener has a speed of 15 meters per second, and the police car that is moving at 45 meters per second, moving away from the listener at a higher speed. All right, so the formula that we're going to use for determining the observed frequency FL is FL equals Fs multiplied by B plus BL divided by B plus BS. All right, so we use B plus BL because the listener is moving towards the source. All right, and for the denominator, we use the plus sign because the source is receding or moving away from the listener. So substituting, we have 300 hertz. That's the frequency of the source of sound multiplied by 340 meters per second plus 15 meters per second divided by 340 meters per second plus 45 meters per second. Doing our math, our answer for FL is 277 hertz. All right, so as expected, the observed frequency is lower than the frequency of the source, in as much as uh, the source, which is the police car siren, is moving faster and moving farther and farther away. So naturally, the frequency that is observed by the listener will be lower. Question number 2. Two train whistles, A and B, each has a frequency of 392 Hz. A is stationary and B is moving toward the right, that is away from A, at a speed of 5.00 meters per second. A listener is between the two whistles and is moving towards the right with a speed of 10.0 meter per second. No wind is blowing. Question letter A. What is the frequency from A as heard by the listener? Question letter B. What is the frequency from B as heard by the listener? Assume that the speed of sound in still air is 344 meters per second. All right, so in our illustration, this is whistle A, which is stationary, and that is whistle B, which is moving at 5.00 meters per second to the right, meaning away from the first whistle. And there's a listener between these two whistles. So the listener is moving also to the right with a velocity of 10.0 meters per second. And the question letter is asking for the frequency that is observed by the listener from the whistle A, or from whistle A. All right. So our formula for that will be FL is equal to Fs multiplied by V minus VL to be divided by B. Why is that so? It is because the listener, all right, the listener is moving away from whistle A. The source of sound is whistle A. So we use the minus sign in the numerator because, as we said, the listener is moving away from the source, to be divided by just the speed of the sound in air, all right, because there is no what we call speed for the source. It is stationary. So when we substitute, we have FL equals 392. This is the frequency of the source of sound, all right, coming from whistle A to be multiplied by 344 hertz. 344 meters per second. This is the speed of sound in air minus the speed of the listener, 10.0 meters per second, to be divided by the speed of sound in air, which is 344 meters per second. Doing our math, we will get as the value for the FL equal to 381 hertz. Again, to be expected that this observed frequency will be lower than the actual frequency of the source of sound because the listener is moving away from the source. And for question letter B, we use this formula. FL equals Fs times V plus VL all over V plus Vs because we use V plus VL because the listener is moving towards whistle B. Whistle B now is our source of the sound. And in the denominator, we also use B plus Bs because the source is moving away from the listener. And substituting, we have 392 hertz multiplied by, all right, the sum of the speed of sound in still air plus the speed of the listener, 344 plus 10.0 meter per second, to be divided by 344 meter per second, and the speed of the, what you call, source, all right? And doing our math again, we will have our FL that is equal to 398 hertz. So we also expect that the frequency observed by the listener would be higher, right, compared to the frequency of the source of sound because uh, you will notice that the speed of the listener is 10.0 meter per second, whereas the speed of the source is only 5.00 meter per second. So in other words, as time passes, the listener becomes closer and closer to the source whistle B. And we expect that the frequency or the pitch of sound that he observes will be higher than the actual frequency of the source. Right? 398 hertz is higher than 392 hertz. Question number 3. A sound source emitting at a certain frequency moves towards an observer with a speed of 5.0 meters per second. The observer also moves away from the source with the same speed and observe a frequency of sound equal to 450 hertz. Question is, what is the actual frequency emitted if speed of sound in the area is 344 meters per second? Alright, so the solution to this problem is based on the formula FL is equal to Fs multiplied by V minus VL all over V minus Vs. Alright? Why this formula? Or why are we using V minus VL? It is because the listener is moving away. Right? The observer or listener is moving away from the source. And why in the denominator? Why are we using B minus Bs? Because the source happens to be moving towards, all right, the listener. So we are using B minus Vs. But what is being asked actually is the actual frequency Fs. All right, not FL but Fs. FL is actually given, and Fs is the unknown variable. So we isolate Fs and come up with this working equation. Fs will be equal to Fl multiplied by V minus Vs divided by V minus Vl. Substituting, we have for Fl, it's 450 hertz. Okay, the speed of sound in air is 344 meters per second, and the speed of the source is 5.0 meters per second. Divided by 344, the speed of air, sound in air, minus the speed of the observer or listener, 5.0 meters per second. Doing our math, we will get the value for Fs equal to 450 hertz. All right. So you will notice that the observed frequency Fl as well as the frequency of the source of the sound are the same, 450 hertz. All right. Why is this like this? It is because we say that the two, all right, the source of the sound and the listener happen to be moving at zero relative velocity relative to each other, right? They are moving with the same velocity. And because of that, there will be no shifting of frequency that will be observed. Strictly speaking, we say there is no Doppler effect happening in this situation. For our last question, question number 4, stationary police car emits a sound of frequency 1200 Hz that bounces off a car on the highway. The police car is right next to the highway, so the moving car is traveling directly towards it at 7.0 meters per second. Question letter A. What is the frequency of the sound that bounces from the car? Question letter B. At what frequency does the sound return to the police car? Use V equals 344 meters per second as the speed of sound in the area. A. This question involves what we call a double Doppler effect. All right. The first part of the what we call double Doppler effect is for us to consider the police car as the source of sound while the car as the observer or listener. So the formula for determining the observed frequency FL, that's just equal to Fs times B plus BL over V. All right. This is because the listener, which happens to be the car, is moving towards the source or the police car. Hence the positive sign in the numerator. Right? In the denominator, there is no speed of the source. It is stationary. So we just divide the whole thing by V. Substituting, we get 1200 Hertz multiplied by the sum of 344 plus 7.0 meter per second, and to be divided by 344 meter per second. Doing our math, we will get the value for the observed frequency FL equal to 1224 Hertz. So this is the frequency of the sound that bounces from the car. For letter B, we will consider the police car as the listener, observer, while the car as the source. All right? And in our formula for determining FL, which is equal to Fs times B divided by B minus Bs, all right? The frequency of the sound that bounces from the car equal to 1224 Hertz is what we are going to use now here in this letter B equation, Fs. And since the police car is now the listener, all right, which is stationary, so there is no what you call speed for the listener in the numerator. But in the denominator, we subtract from V the speed of the source, which this time is considered the car. Okay, why minus? Because the car is moving towards the listener. All right. When we substitute, that's FL equals 1224 Hertz to be multiplied by the speed of sound in air, 344 meter per second, and divided by the difference between 344 and 7 meters per second. Doing our math, we will get as the value of FL 1249 Hertz. Alright? So this is the frequency of the sound that returns to the police car. Notice that this frequency, the one that returns to the police car, is much higher compared to the original frequency of 1200 Hertz, or even higher than what bounces from the car, 1224 Hertz. So these are the answers to our question number 4, and we are done with our video tutorial. Thank you very much for your indulgence. Thank you very much for watching. Please follow me in my FB page, and please don't forget to subscribe to my YouTube channel.